All right, we're back with a banger. This one is great. We've gone over all the different types of loading, and now it's time to apply them. We got a real problem now with real numbers and a real good attitude about it. So let's get going. What are we gonna do first? That's right, we're gonna sum the moments, right? I encourage you to do this problem along with me and like pause the video and shit like as I go. Okay, to sum moments, we need to know where all of our forces are, right? And we got a bunch of them up here, which is great. But we also need the reactionary ones. And so we have a roller here. We're gonna have an EY reactionary. Rollers only give forces in the perpendicular direction because they roll. So what else? AY, because we got a pin there, so AY. And again, we're gonna have an AX, but that equals 0 because I don't see another x-axis acting force on this thing, so we're gonna call that 0. And one more thing to know about summing moments is about these distributed loads are you also want those to be modeled as just 1 point load, right? And you can do that by right, this is pound over feet, so 300 pound per feet. You can do 300 times 6 because that's the distance that it is distributed over. I have to grab my calculator. So, all right, we got 300 times 6. Great, 1,800. 1,800 pounds right there. Pounds on that, put pounds there. Right, just that the only reason we did that is because it makes it easy to calculate once you start setting up your equations. And where is it acting? Right in the middle of this distributed load. For moment purposes, that's what we're going with. So if it was a distributed load at an angle, it would be, you'd make a triangle and it would be at 3/2 of whatever the length of that triangle is. But with this, we're working with just a straight, even distributed load, so the force is going to be right in the middle of it. Great. I think we have everything we need to sum the moments. So let's go ahead and do that. Where are we going to sum the moments? I want to sum them about A, right? Because they cancel out, get rid of this force, don't gotta calculate it. It gets rid of the X force. We already know it's 0, but still gets rid of it. So I'm going to do, see if I can fit it in here, positive moment, like that. Summing moments about A equals 0. And let's see, that equals, going left to right, our first force there is gonna be a negative because it's trying to spin the bar against my positive sign convention. So it's gonna be a negative 1,800 pounds because that was our total force there. And the distance from A is gonna be 6 plus half of 6 because it's right in the middle of this, right? This A, B, C, D, E, F beam is just chopped up by 6s. Pretty nice. Of course, that's not always the case, but that's what we're working with here. So negative 1,800 times 6 plus 3 is going to be 9, right? And then keep going, left to right, boom, our next thing, a moment. So moments are in pound feet, right? So we don't need to care about the distance from A that moment is. So we're just going to put it in there as plus 6,000, and it's positive because it's going in the same direction as my positive sign convention. And then keep going left to right, EY, boom, there it is. So let's see, it's going to spin the thing in the positive moment direction. So it's going to be a positive EY, and how far away is it? Let's see, 6, 12, 18, 24. 24 feet, right? Yeah, 24. Have to double check on that one. 24. Okay, and then keep going because we're not done yet. Boom, another one. We got it spinning it that way against the moment, positive moment. So it's going to be negative 1200. Don't forget the distance because it's just a force. That's going to be 30, right? 6 times 5. Great. And now, look at that. Only one variable in an equation that's set to 0. So we can go ahead and solve for that. Variable being EY equals 1925. Great. And that is in pounds, because again, it's just a force. 1925. Right there for EY, pounds. Okay. Now we can sum the forces, because we have all the forces except for one, right? So we can set up an equation, one variable, go ahead and solve for it. So let's go. Sum the forces in the y, set that equal to 0, equals, let's see, positive AY, because it's pointing up, and then a negative 1800, and we don't have to worry about distances because forces are just pounds, not pound feet. So there's our negative 1800 going down. Moment is not a force, right? Like in the y direction, so we don't got to worry about it. And then plus EY, which was 1925. It's going up, and then minus the downward force, 1200 pounds. Once again, one equation, one unknown. Go ahead and solve for it. AY equals 1075. Great. And let's put that up there. 1075, and that's pounds. Great. All right, now we have all of our forces. We know all of them, even the reactionary ones. So we're good to go. Good to start graphing this, right? Shear and moment. So let's do it. Here we go. Forces create shear, right? So work left to right. What's our first force? AY. Great. And how big is it? Well, it's right there. We just found that out. It's 1075. So we're going to go right, let's just go right there with it. It doesn't really matter, right? As long as you label it. So 1075. There we are. That's our first jump, because that's right at the beginning. And then over this next 6 feet, nothing happens, nothing's going on, and then boom, we run into our distributed load. For the equations, we had it nicely organized into one force, but that's not the case here on the graphs. On the graphs, we have to respect that it is a distributed load, and it is straight across. So remember in the last, or was that the last video? I don't know, but we talked about being a linear line here, right? Because this is constant, and it's the integral of a constant. So we're gonna do a linear line that goes down, because this is negative. It's negative force, so it's gonna make negative shear. It's gonna go downwards. The question is how much, right? So the way that we figure that out is get your calculator, and right? This is 300 times 6 feet, and we already did that. It's 1800. So we know the total amount of force that's gonna happen. So we know that that's how much we're gonna end up going down. This is where we need our calculator, right? We go from 1075, that's the value that we're already at. We're already up there. And now we're going down 1800. So we're gonna go 1075 minus 1800. And that puts us at negative 725. So that's where we're gonna go down to. Darken that up. Negative 725. Great. So there we are. Actually, sorry, I'm just perfectionist. I want this to look better. I'm just gonna go to like there. Yeah. Okay. Negative 725, right? Because 1075 minus 1800 gives us negative 725, and it's linear because this is constant. Great. Now from there, what happens? Working left to right still, nothing happens, nothing happens. Here we are at our moment. Moments don't really affect shear, so nothing happens, nothing happens. Boom, okay, we hit EY, great. Forces create shear. So go back to our calculator. We already have this negative 725 in there. That's this value that we were at riding along at a constant down here. And then we hit this positive EY, so we're gonna add 1925 because EY is 1925. Boom, that puts us up. We're gonna jump up all the way up to 1200. Negative 725 plus 1925, positive 1200. That's where we are. And now what? Keep working left to right. Nothing happens. Nothing happens until boom, we're here at our final force, our final point. And look at that. It's 1200 pounds. And where were we? 1200 pounds. So this is acting down. We're going to jump down 1200 and end back up at 0. Perfect. That's where we want to be. We ended up at 0, so we know we did it right. That's a good check, but there are ways to mess it up and you'll still end up at 0, so you still want to like go through your math and just make sure. But there we go. Shear. Now let's do moment. This is a little bit more exciting, a little bit more going on. We're gonna have a parabola in here somewhere because of this here line, right? Linear line integral would be a parabola. So let's get it going. I work directly off of the shear diagram. Right? So knowing that we're starting at 0, there's no moment here, right? Because it's just a pin, it's not a fixed wall connection, so there's no moment. So we're gonna start at 0. And then what, right? We're gonna go up the distance, or we're gonna go up, not the distance, but the area that this chunk is here, because we're just gonna do it, we're gonna take it 6 feet at a time. So we're gonna take this 6 feet at a time. When we have 1075, that's the height, times the distance is 6, gives us 6450. So that's where our moment is going to end up. Let's put it like there, right? We're going to go straight up to 6450, and it's linear because this is constant, right? Cool. Here's where it gets a little tricky, because now we're dealing with this slope line here. And there's a couple different ways to do this. I'm going to show you the way that I think makes the most sense. Some people will do it with using similar triangles, because this is a triangle here, there's a triangle there. That confuses me. What I do is I see this as a graph, right? Y and X axes. And I see this is a line, right? And I can find the slope of that line, right? M, the slope is rise over run. So how much did we rise over this whole area, right? Because we're trying to find, sorry, I should have explained this. We're trying to find this distance, because that'll tell us where our parabola zeroes out, because that's where it crosses the x-axis, so that's 0. So then our parabola should have no slope at that point. We just need to know where that is, right? So we're looking for that distance, this distance here. Sorry about that. That's what they use similar triangles for. That's what I'm doing now. The slope of this line, back to it. The slope of this line is rise over run. So how much did we rise? It was, this is down 725, so 725 plus, because I'm looking for magnitude here, 1075, 1075. That says that the rise, we rose 1800. Okay, so 18. All right, sorry about the interruption. My phone ran out of storage. Great. All right, so here we were, M, slope. I don't know where it cut out, so I'll just re-explain. I'm doing this now so that I can find this distance. This distance is important to see where our parabola zeroes out, right? Where this crosses the x-axis. That's important. We need the height there for full credit. So that means we need this distance, right? Some people do it with similar triangles, these two similar triangles. That confuses me. I'm gonna do it the way I know how to do it, which is the slope of this line. I see this as a graph with a line on it that I can find the slope of because I know the rise, right? And I know the run. So let's see, I'm looking for magnitude here, so 725 plus 1075 gives me 1800 is the rise, times our distance, our run is 6, or sorry, 1800 is our rise over 6, more like it. Gives us our slope is 300, right? So M is 1800 over 6, slope is 300, right? And so now we're going to put it in an equation for y equals mx plus b. We know m, we just did that, is 300, x plus b. Now what's b? What I like to do is I like to bring this y-axis over to the point where I'm looking at. I'm looking at the start of this line, and I'm going to move the y-axis to right here, which tells me that the y-intercept is 1075, right? Because we just went straight over from 1075. So b, the y-intercept, 1075, right? That's where our slope starts. So that's what we care about. All right. Now, how do we find x? So if the y-axis is here, right, that's where it starts, and we want x. X is the distance right here. We can set y to be 0, right, because that'll tell us where this thing crosses the x-axis. So 0 equals, did that make sense? Did I explain that well? I feel like I didn't. Like, I feel like this is important. So I want to make sure you understand. If this is your graph at y and x, this is your line at 1075 is the y-intercept, and the slope is, sorry about that, negative. What am I doing? It's negative. You gotta catch me on that. Hope you caught that. Hope you were like, that should be negative. Okay. Probably screaming at me through the phone. Negative, right? Because it's going down. What am I doing? All right. Set y to be 0. That'll tell us that x distance, where the graph crosses the axis there. So 0 equals negative 300x plus 1075. Solve for x. solve for x. Negative 1075 divided by negative 300. Great. 3.583. So, what is that number? That is this. That is that distance. 3.583. Hope you can read that. Okay, so why do we need that? Well, since this is linear, our next thing is going to be parabolic on our moment diagram. And how do we find out where that thing's going, right? So, we know it's going to go up, at least until this, right, this point, because this is positive area. It's above the axis. So we know it's going to go up. And we know it's going to start up and slowly level off because this is very positive and slowly goes to 0. So the slope is going to be very positive and slowly goes to 0. It's going to look like that. All right? A little bit of a curve in there. I don't know if you can see that, but there is. Okay, great. So we know what that part looks like. Now, what is this point? How high up did we get? I'm sorry, I didn't put that last value on there, which was 6450, right? Remember that? Because that's the area of this. 1075 times 6, 6450, that's where we are there. Okay. Plus the area under this curve is how much more we go up with that parabolic line. So what is the area under this curve? Well, it's a triangle, so we can do 1075 is the height times the distance we just calculated is 3.583, right? And then that divided by 2. So 1925 is how much more we went up since this point. So we got to add that to 6450. And we end up at this point, the peak of our parabola is 8375.86. Cool. Now what? Keep on working left to right. Our parabola is going to start going down because this here is negative area. And how much is it going to go down? Well, again, let's do the area. That's 725 times what is the distance. That's going to be, right, this total distance is 6, and we're interested in this distance, so we're going to minus that distance. So I'm going to do 6 minus 3.583, 1752. Okay, and this, again, is negative area. Oh, wait, divided by 2. Sorry about that. It's a triangle. So, yeah, so this is negative area. It's going to go down, right? And it's going to go down from that value. So 8375.86, our last point, minus the amount that it's going to go down, the area of this triangle. And that's going to put us at 749.9 point. I'm just gonna say 0.7. That's pretty close, right? Okay. Now what? Keep on working left to right. We got this negative area, and it's constant. So a constant, what's that gonna be? Yep, linear. You got it. So we're gonna have, and it's negative, so it's gonna be a negative linear slope. And it's going to go down the amount this value gives us. So that's 25 times how long is 12. 725 times 12 is 8,700. So it's going to go down 8,700 at a constant rate from 7499.7. So 74.99, oh, sorry, not point, what am I doing? 7499.7 minus the amount of this area, which was 8,700, puts us down at, over this whole distance, gonna go dip beneath the x-axis, and that's a straight negative line there. Sorry if it wasn't very straight. I'm gonna try that again. Go straight down. You get the idea. It's linear. It's a straight line. To negative 1200. All right? 1200.3, but I'm just going to say it's negative 1200. And you'll see why. Because, what do we got here? Oh, you know what? What did I miss? What did I miss? I'm doing moment diagram here, and I'm so focused on this shear diagram. I'm following the diagram, right? So I'm thinking, okay, you know, it's going to go down constantly, but what did I miss? I missed something. I'm working with moments. I'm going off of the shear diagram, so I missed the moment applied on the member, because that doesn't affect the shear diagram. So you got to watch out for that. You can get tunnel vision by working on these, and then you'll get the wrong value in the end. You'll be like, what happened? That's what happened. You missed the applied moment. So applied moments in a moment diagram are going to make a jump, right? Because it's a moment diagram, and there's your moment. So it's going to jump right to where it's going, right to where what's going on. And it's going on right here is when it's happening, right? Just above the x-axis there. Or not, that's arbitrary. I just drew that line. Doesn't really matter. Point is, it's going, actually, it does matter. It does matter. All right. I'm all over the place. This is why it matters. All right. Calculate this area first. Sorry about that. Calculate that area first. That's going to be 725 times 6 is 4350. That's the amount that we're going down from 7499.7. So 7, I'm just going to round that up to 7,500, right? 7,500. Does that make sense? 7499.7 to 7,500. So that was the value that we were at minus the amount that we went down because of this negative area. So minus 4350. 3150. Okay. So that's what we went down to, and that is positive. So that is above the x-axis there. 3150. Great. Now time for that jump because of this applied moment. Applied moments make jumps happen in moment diagrams, right? That makes sense. It's a moment diagram. Cool. And it is going in the negative direction. That is negative moment when it comes to the moment diagram, right? Let's put that little sign convention on there right now. Forgot to do that in the beginning, but just so you know. So that's going to be a jump down 6,000 pound-feet. So our value here, 3150, from where we were, minus 6,000. You always work from where you were, add or subtract the thing that you're dealing with, right? From where you were in your work. So that's going to jump us down to negative 2850. Perfect. Okay, so from there, working left to right, we still have this negative area, so we still got to account for it. And it's at, again, negative 725. So negative 725 times distance is 6. 4350, that's the amount that we're going to go down. So from negative 2850, right? That's where we are now. So negative 2850 plus our answer, which was negative 4350, is going to bring us all the way down to negative 7,200. Can you see that on the page? Yes. Okay, great. Okay, negative 7,200. Perfect. That's where we're at. Keep working left to right. What do we have? This positive area, right? And it's constant, so we're going to have a positive linear line there. And again, we're towards the end now, so there's nothing else going on. You could assume that it just goes straight back there, but we're gonna prove it, right? 1200, and this is also a good way to check. So 1200 is the amount times the distance is 6. And look at that, we got 7200 positive, because this is a positive area, right? And look at that, negative 7200. So again, we always end up back at 0. This is going to bring us up a positive 7200 from negative 7200 back to 0. There we are. Color it in. And that's an A plus shear moment diagram right there. All right, see you in the next one.